speakers today. Let's get right into it. So our first speaker will be Dr. Peng Hang from Tongji University. Dr. Hang serves as an associate editor of IEEE Transactions on Vehicular Technology, among other top-tier journals. And also he served as an associate editor, session chair, and also session organizer of many international conferences. So his topic today would be cooperative decision-making for CAVs at unsynchronized intersections, a multi-agent reinforcement learning approach with attention and hierarchical game priors. So Dr. Hang, the floor is yours.
Dr. Hang, you can share your screen now.
Okay, can you see my screen now?
Yeah. Yes.
Okay. Thank you, Dr. Li's introduction. Hello, everyone. My name is Peng Hang from Tongji University. Today, I'm very glad to share the study of cooperative decision-making for CAVs at unsynchronized intersections, MARL approach with attention and hierarchical game parallels. I will introduce my work from the following parts. First, I'll give a short introduction of this study and then the methodology. The third part is experiments and results analysis. And finally, I will give a short conclusion and introduce the future work. In recent years, autonomous driving technologies have been studied and applied to some cars. For example, the robot taxi, robot bus, robot truck. However, faced with some complex scenarios, there still remain some challenges. For example, in this figure, we can see that the driverless cruise cars caused a traffic jam day after mass expansion approved in San Francisco in August. Nowadays, autonomous vehicles cannot deal with some very complex scenarios, especially to deal with the interaction with human drivers. And in our opinion, cooperative driving can deal with this issue. In this study, we mainly focus on a very complex scenario as unsynchronized intersection, in which human driving vehicles and autonomous vehicles created a mixed traffic environment, very complex, and with many focus on the study of cooperative decision-making for CAVs to enhance driving safety and improve the travel efficiency. As we all know, in SAE 103016 report, the autonomous driving has been divided into 5 levels. From level 1, the driver assistance, to level 5, pure driving automation. Actually, 3 years ago, SAE has proposed the concept of cooperative driving automation we call a CDA. CDA has 4 classes. Class 1, Class A is status sharing, means here I am and what I see. Class B, intent sharing, it means this is what I plan to do. And Class C, agreement seeking, it means let's do this together. And Class D, prescriptive, it means I will do as directed. The 4 classes can support the cooperative driving automation. It aims to improve the travel efficiency and driving safety, especially in some very complex driving conflict zone. In the United States, the CAMA project has been conducted many years ago and created the CAMA platform for CAVs. With V2X technology, autonomous vehicles can share their intention, their status with each other, and realizing the cooperative decision-making or control. For example, the right to short videos, platooning control for CAVs, and cooperative merging for CAVs. This scenario and cases are conducted by Kama, but however, these test cases are not very complex. In our team, we have studied cooperative driving research for many years, and we can see a short video. It is a test of one robot taxi in China, a test in Tongji University, a test is autonomous systems driving system performance. We created some complex scenarios with simulation software, and it creates a real vehicle in the loop test. The real vehicle can interact with simulation cars, and these scenarios are very complex. For example, the left turn, unprotected left turn, the unsynchronized roundabout, and the unsynchronized interaction scenarios. Based on the test results, we can find that nowadays the autonomous driving system cannot deal with these complex scenarios very well. The autonomous vehicles usually show some negative behaviors. For example, waiting for a long time at an unsynchronized intersection, and this results in the decreasement of the travel efficiency. To this end, we designed some cooperative driving systems to deal with this issue. We can find another short video. We built different kinds of cooperative driving algorithms based on the V2V and the V2I technologies. Vehicles can share their states and intentions with each other and cooperate to realize the cooperative decision-making and control to deal with some very complex driving scenarios. And from the test results, we can find that with the cooperative decision-making algorithms, vehicles can improve its intelligence compared with the traditional single autonomous driving system. This is some work we have did in last 3 years. Come back to this study. We know in recent years, many researchers have applied some different kinds of methods to realize cooperative decision-making and control. For example, the game theoretical approach, including a level K game, a leader for a game, and the learning-based method. For example, the multi-agent reinforcement learning, MARL, and some optimization-based methods, especially for MPC. MPC have been widely used in the platooning control for CAVs. However, each method has its advantage and a disadvantage. I will not introduce in detail. To overcome this disadvantage, in this study, we proposed a multi-agent game parallel attention DDPG algorithm to improve efficiency and safety performance for CAVs. Firstly, we transformed the CAV cooperative task into MARL problem using the MADDPG algorithm based on the CTDE. And secondly, we combine the attention mechanism and the level K hierarchical game together to create the attention game parallel for the safety supervised model design. And then based on the two parts, and it yields the game parallel attention DDPG model. I will introduce this model in detail. In the scenario setting, we focus on unsynchronized intersection environment. This intersection is commonly seen in China, four-way, single lane, cross-lane, cross-shaft. one AV vehicle enters each direction, coordinating through the intersection. For AVs speed, position, and destination are randomly generated in this scenario. For CAVs, vehicle states need to vector, and the CAV strategies mainly focus on acceleration, constant speed, and deceleration. In the reward function design, we consider the clean reward, efficiency reward, and arrival reward. For the human drivers setting, we consider the lateral behavior is controlled by a mobile model, and the longitudinal behavior is controlled by IDM model. In the lower level motion control, the human driver vehicle is controlled by a PID and PID controller, and based on the bicycle model. Besides, the speed motion prediction module is also designed based on the assumption of simple constant speed, 3 seconds prediction. Since our model is based on MADDPG, so I want to introduce MADDPG briefly. MADDPG is an extension of DDPG in multi-agent tasks. The framework is based on the centralized learning and distributed execution. And each agent is trained using the actor critical framework. During training, a global critical guides the actor while drawing and testing. The actor only has access to local observation to take actions. This figure shows the MADD framework, mainly based on the centralized training and distribution execution architecture. The original policy network of the MADDPG is a simple MARP. Our first task is to improve the policy network, designing a new attention-based network architecture to replace the existing MARP. We adopted encoder attention decoder architecture. For each agent, the input is encoded, passed to the attention layer, and then decoded to produce the specific action, resulting in our attention MADDPG model. Next, based on the results obtained from the attention mechanism, we calculated the game theoretical parallels and passed them to the agents. We modeled this entire process as the attention level K game theoretical parallel model. This involves 2 steps. The first step is to use the attention mechanism to select interactive objects, and then calculating the attention each AV pays to all surrounding vehicles using the policy network to filter the interaction objects. After selecting the interactive objects, we then determine the right way based on the level K game theory. We post that more attention on vehicle significance is importance, granting it a higher priority. This process involves calculating the total multi-head attention received by all CAVs and HVs, followed by a descending order sorting. Once obtaining such parallel information, we designed the module to help the algorithm rapidly learn this parallel knowledge. We developed a safety supervised module based on level K game theory. For each CAV, we first predict the future trajectories for the CAV and surrounding HVs over T steps, then assess the conflict risk for each candidate action of the CAV, and finally compute the optimal action to correct the agent's behaviors. And this figure shows the MADDPG modules framework. The many have 2 two modules. The low module is the attention MARL module, and the lower is a level K priority-based safety inspector. And based on the design algorithm, we designed some cases to evaluate the performance. We designed 3 cases. The first case is a CAV only environment, 4 CAVs only. And the second case is a mixed driving scenario, 4 CAVs and some human-driven vehicles with the same driving style. We call it the homogeneous mixed driving environment. And the third case is also a mixed driving environment, 4 CAV and some human-driven vehicles with different kinds of driving styles. And we also compared 3 kinds of algorithm in the 3 cases. A baseline algorithm MADDPG and the improved baseline algorithm attention MADDPG, and our proposed algorithm MAGADDPG. The first case is a CAV only environment. From the test results, we can find that the proposed MAGADDPG algorithm shows a good better performance than other 2 algorithms. Besides, the attention mechanism improves the motor's performance, but with limited effect. Finally, using the parallel models and the safety inspector significantly improves the performance. The second case is a mixed driving environment, including CAVs and homogeneous HVs, which means these HVs have the same driving styles. From the test result, we can see some similar conclusion. Firstly, the proposed MAGADDPG algorithm shows a very good performance compared with other 2 algorithms, baseline algorithms. Besides, the effect of the attention mechanism is more significant. At the same time, the safety inspector can further improve the algorithm's performance in a mixed driving environment. The next case is also a mixed driving environment. The difference is in these cases, different kinds of HVs have different kinds of driving styles. So, including the aggressive, normal, and conservative driving styles. From the test result, we can also find that the proposed MAGADDPG can deal with different kinds of driving styles and shows better performance than other 2 algorithms. Safety inspectors significantly improves the performance of the algorithm in a heterogeneous HV mixed driving environment. From the motor performance analysis results, we can conclude that the proposed MAGADDPG algorithm performs well in multiple scenarios and has good decision-making capability in complex interactive environments. Besides, we also analyze the results from different kinds of driving performance, including driving safety, efficiency, and comfort. The first in performance is safety. We use PET to evaluate the safety, the vehicle's safety. From the analysis results, we can find that the average PET or the proposed MAGADDPG is improved by more than 16% compared to the traditional MAGADDPG algorithm. Besides, the MAGADDPG is the most aggressive during the interaction process and has worse safety performance. And the proposed MAGADDPG algorithm is safest among the 3 algorithms. As to travel efficiency, we can also find that MAGADDPG algorithm has the highest average speed with more aggressive speed adjustment, result in dangerous interactions and frequent clears. Compared with MADDPG, the attention MADDPG algorithm has the lowest average speed, but still pass a lower speed after passing the confidence zone, result in a lower travel efficiency. Compared with the above two algorithms, the proposed MADDPG algorithm can decelerate in a timely manner when entering the intersections to ensure the interaction safety, and then accelerates the appropriately and after passing the conflict point, which means they can consider the safety and efficiency very well. As to comfort, we use the longitudinal acceleration to evaluate the comfort performance. We can also conclude some similar conclusions. The MADDPG has extensively drastic acceleration and deceleration when passing the intersections, which significantly affect the comfort. However, compared with the MADDPG, the acceleration and the deceleration, the amplitudes of the attention MADDPG algorithm and the proposed MADDPG algorithm are more gentle and ensuring the better comfort. Here we can see some demos. Left-chain CAV interacts with straight-going HV. CAV interactions with our proposed MADDPG algorithm. We can find that CAV can learn to balance the safety and efficiency and interact with different driving styles HV, and finally passing through the intersection smoothly. Finally, I'll give some conclusions and introduce the future work. In this study, we modeled the CAV cooperative problem as a MARL problem, and established a game attention parallel model based on attention mechanism and hierarchical game. Besides, we built a GA parallel and a safety inspector model to create a MADDPG model for cooperative decision-making. We set up different kinds of experiments to evaluate the performance of the proposed cooperative decision-making algorithm. The test results show that the proposed MADDPG algorithm performs well in terms of safety, efficiency, and comfort. In our future work, we will apply the proposed algorithm to the real vehicle test. Okay, finally, I want to say thank you to all the authors, including the first author, my student Liu Jiaqi from Tongji University, and the two co-authors, Dr. La Xiaoqiang from the University of Cambridge, and Dr. Huang Chao from the Hong Kong Polytechnical University. And finally, I say thanks to our top team leader, Professor Juan's support. Here I show some related papers, publications related to cooperative autonomous driving and interaction modeling for your reference. Okay, that's all. Thank you.